In the second part of section 5.3, we investigate and discover the importance of independent random events. So independence as it applies to probabilities and independent events. All right, so we're going to come up with a rule for determining whether two events are independent, and then we'll use the multiplication rule, the general multiplication rule, for calculating probabilities when events are independent. All right, so knowledge that one event has happened when that does not change the likelihood of another event happening, then we consider the two events independent. And so one way to test if two events, A and B, for example, are independent, then the probability of A given B, so the probability of A given B, would really just be equal to the probability of A. That means A does not depend on whether B happened or not. So probability of A given B and the probability of A should be the same. Same thing if probability of B given A is the same as probability of B. If either one of those things happens, then we know the events are independent. All right, and then if they are independent, then we can, instead of using the probability of B given A, we can just substitute that with probability of B. So that means the probability, the general rule down here for the probability of A and B is the probability of A times the probability of B, given that A has already happened. But since we're now saying, what if the events are independent, then we can take out this probability of B given A and just put it in as probability of B. So we simply multiply the probabilities of the independent event. So if the events are A and B are independent, then the probability that they both occurred, so probability of A and B, or the intersection of A and B, is simply the probability of A times the probability of B. All right, so let's see. How can we use this idea and this rule to test whether or not two events are independent? So if is there a relationship between gender and the relative finger length? So a two-way table shows the gender of each student and whether the finger, and which finger was longer on their left hand. So the index finger, that's like your pointy finger, and then your ring finger, the finger that's next to your pinky. We call it ring finger because that's the finger that you often put your ring on. All right, which one is longer? So we can see here in our table, for some people, the index finger, the pointy finger, finger you use to point with, the index finger is longer. Some have a ring finger that is longer, and some have ring finger and index finger that are the same length. All right, so the question we want to investigate is the event being female and having a longer ring finger independent? So we're just going to use the rules about, if they are independent, then the probability of your ring finger being longer, given that you're a female, should be the same as the probability of just a ring finger. And we can get these probabilities by looking at the counts in our two-way table. So the probability of a ring finger given you're female, so given you're female, that means we're in this column of our table. And so probability of a ring finger given female would simply be ring finger longer is 80 for 82 people, divided by the total, which is 212. And then the probability of a ring finger being longer, that would just be the total ring fingers that are longer divided by the total in the table. And so when we divide those, you see that one is something close to 39%, the other one is close to 52%. So no, these are not the same values. And so that tells us that the event having a ring finger longer and the event being a female are not independent. So knowing that you have a ring finger that is longer, or knowing that, doing it this way, knowing that you're a female, we know that you're less likely to have a longer ring finger than the population as a whole. So knowing that you're a female helps us to determine that your ring finger is less likely to be longer. And so one sort of helps us predict the other. So these are not independent. Okay, so these two probabilities are not equal. So the event female and has a ring finger that's longer are not independent. So knowing that a student is a female makes it less likely that their ring finger is longer, and we can when we know that because they're not independent. All right, so let's look at some more independent examples and how we can do calculations and probabilities. So for this example, I'm using the Challenger shuttle disaster from 1986. This is the first of, I think, two Challengers, two shuttles that exploded. This one exploded in the takeoff process. The other one disintegrated or exploded, if you will, as it was re-entering the atmosphere. So in this one, the very first one in 1986, it was determined that it was the O-ring joints in the solid rocket boosters. So the shuttle is made up of the shuttle, and then there are two solid rocket boosters kind of on the side of this brown hydrogen tank. So this tank is filled with liquid hydrogen, and these things are what we call solid rocket boosters. They're filled with solid fuel, not some kind of liquefied gas or liquid. And so these solid rocket boosters are assembled they're manufactured in a plant and then sent to Cape Canaveral, and then they are assembled in their 4 parts, and they're assembled. So they have 3 joints, and in those joints there are these O-rings, and you can see here that these O-rings, a little, like a third of an inch in diameter cross section, but they're rather large. They're about 12 foot. These solid rocket boosters have a rather large diameter. And so this is like the design. This is actually the new redesigned O-ring joint using 3 O-rings. The original design only had 2. All right, and so it was discovered that these 3, that it was the O-ring joints that were losing their seal and letting gases escape, and that's what was that had caused the Challenger explosion. All right, so this design here is actually the original design. It only had 2 O-ring joints. And you can see here, this is a little blow up. If you look here, the blow up is right here. And so the problem was during cold mornings in Cape Canaveral, and quite honestly, there's not often cold mornings, but on cold mornings, the rubber gaskets were sort of cold and brittle, and so they let fumes and gases escape these joints on occasions. All right, and so again, there are 3 of these O-ring joints with multiple O-rings in them, but 3 joints on each of the solid rocket boosters, and so that means there are 6 O-ring joints. All right, and so this diagram shows a little bit of like a cross section. You can kind of see here. Here's pictures. This is the O-rings. They found the solid rocket boosters in the bottom of the ocean, and they basically brought them back up to examine them to see what exactly happened. And so they found remnants of the O-rings, and so they show here cutaway pieces of it, and so you can see what the O-ring is supposed to be, but how much of the material was actually left. A lot of it burnt away, allowing the gases to escape and then those gases and flame is what caused the disaster. So you can see here in this picture, this is sort of a diagram of the shuttle as it's positioned here, and you can see where the arrow is pointed, the gases are starting to escape. So these are kind of time-lapse photography, frame by frame, of the flame getting bigger and bigger. And you can see what's right next to that solid rocket booster where the flame's coming out um, is the is that big hydrogen tank. And so this is what happened: is the flame got big enough so that it ignited the hydrogen tank, and the whole thing exploded. These two trails going off here are actually the solid rocket boosters that disengaged from the rest of the shuttle and just took off, willy-nilly through the air. Don't believe they ever did find the cabin with the astronauts in it. Okay, so let's do some probabilities involving this situation. All right, so following the the Space Shuttle Challenger disaster, it was determined that it was the failure of O-ring joints in the shuttle booster rockets, so solid rocket boosters, that was to blame. Under cold conditions, it was estimated that the probability of an individual O-ring joint would function properly was about 97.7%. So that sounds like a pretty high percentage. So now, and that's again, it was much higher than that when it was normal, Florida, usually it's what, 60, 70, 80, 90 degrees. And so when it was warm, it wasn't a problem. But when it was in a cold morning, I think that particular morning there were some icicles on the shuttle. So it was down, near freezing or close to it. So assuming that, here's the question we want to investigate then. So assuming the O-ring joints succeed or fail independently. So in other words, if one O-ring joint starts failing, it's not going to cause another one. They're all independent, and they fail or succeed independent of each other. So assuming that the O-ring joints succeed or fail independently, what is the probability that all six will function properly? In other words, that none of them fail, right? So we don't want any to fail. If one fails, it's really just as bad as two failing, because, we only need one for the thing to explode. Two would just be, that much worse. So we need all six to function properly in order for this shuttle to take off properly. All right, so we want to know what's the probability that joint 1 is going to be okay, and joint 2, and joint 3, and joint 4. So there are 3 O-ring joints in each of the 2 solid rocket boosters. So we need all 6 joints to function properly. All right, so we just talked about the multiplication rule. If they're independent, then how can we calculate all these probabilities? Is we simply multiply them all together. So the probability that the first joint's okay, and the second joint, and the third joint, and so on. And we know from up above that the probability that an O-ring joint works properly on a cold day is 97.7%. So we simply multiply all those together, and we get about 87%. So that means there's an 87% chance that the shuttle would launch safely under similar conditions when it was cold out. So that doesn't sound like really good conditions. I mean, a probability actually. So that means, 87% chance it'll work. And that means 13% chance that it's not going to work. That at least one O-ring joint is going to fail, and that's 13%. So, I mean, I think that if you had a 13% chance that your car would explode on your way to school, I think we would all start walking to school a lot more. All right, so let's look at another example. In baseball, a perfect game is when a pitcher doesn't allow any hitters to reach base in all 9 innings. So historically, pitchers throw a perfect inning, an inning where no hitters reach base, about 40% of the time. So about 40% of innings are an inning in which no batter reaches a base. So we'll call that a perfect inning. So to throw a perfect game, a pitcher would need to throw 9 perfect innings in a row, right? Not allow anyone for the whole game. A typical game is 9 innings. We're going to just ignore the possibilities that it would go to overtime and go into extra innings. All right, so here's the question. What's the probability that a pitcher throws 9 perfect innings in a row, assuming, of course, the pitcher's performance in any inning is independent of his performance in any other innings? All right, because would have to have all of the outcomes being independent of each other, all those events, or all those innings performances would be independent. All right, so that means he'd have to have an inning 1 be perfect, and inning 2 be perfect, and so on up till we get 9 innings that are perfect. And so probability that inning 1 is perfect times the probability that inning 2 is perfect. And we're assuming, of course, that happens about 40% of the time. So we would simply just do 0.4 times 0.4 times 0.4, or up 9 times, or 0.4 to the 9th power. So you can see this is really a small occurrence, right? 0.00026, or about, I guess we move the decimal place, 0.026% of the time. All right, so now there are 30 teams playing 162 games per season. This means that we would expect, if it happens as often as what we just calculated, we would expect 30 teams playing 162 games times the probability we just calculated. We would expect about 1.3 perfect games per season. So if any of you are baseball fans, you know that that isn't anywhere close to how often it happens, right? You don't get one perfect game every season. As it turns out, it's every couple seasons at most. However, in baseball history, perfect games are much rarer. They occur once every 4 or 5 seasons on average. And so what is the discrepancy? Why is our calculation saying that we should have 1.5 perfect games or 1.3 perfect games per season, but we get much less than that? We only see them every 4 or 5 seasons. So probably that might have something to do with the fact that we have made an assumption here that a pitcher's performance in one inning is independent of another, and so probably we would call into question that independence. In order to do these multiplication, in order to do this calculation, of course, we have to use a general multiplication rule. And if they're not independent, we can't really do that. So probably our assumption of independence is probably called into question here. All right, so the next thing I want to talk about, and students confuse these a lot, is independence versus mutual exclusivity. And so to help you understand this and the relationship, I need to go back and give you a little bit of an honors geometry lesson. So there's some topics in honors geometry that back in the day when I used to teach honors geometry, we covered them, but as it turns out, they don't cover them these days. So I'm going to give you a little bit of a background in some terms for honors geometry that will help us understand our relationship between the term independence and mutually exclusive. All right, so first we want to talk about conditionals. And so a conditional, we often will use symbols to indicate conditionals. A conditional, if you remember, is just an if-then statement in geometry. So a conditional is something like if P, then Q. So sometimes we say if P is true, then Q is true. Sometimes we write it as P arrow Q, and sometimes we will say it as P gives you Q. So in other words, if P is true, then Q is true. And so here's an example. If two angles are 90 degrees, then they are congruent. And so that is a conditional that happens to be true. So if two angles both are 90-degree angles, then we know, of course, that they are congruent. All right, so in geometry, we also have another term. We have conditionals. We also have converses. And so the converse of this statement is not true. And so the converse means you take the first part and you make it the second, and you take the second and you make it the first. So the first statement, if two angles are 90 degrees, then they are congruent. So now we reverse it. Q becomes P, P becomes Q. So the converse for this particular conditional would be, if two angles are congruent, then they are 90 degrees. So you can kind of, if you think back, two congruent angles do not necessarily have to be 90 degrees. So that is a false statement. So the converse for this particular conditional is not true. Sometimes converses can be true, but for this one, they are not true. All right, so then we have another term. So we have conditional, we have converse, and we have another term called the contrapositive. Now, you've been taught conditionals, you've been taught converses, but you probably were not taught contrapositive. It used to be part of our curriculum in honors geometry, but for some reason they haven't taught that in years, at least not at Montclair High School. So the contrapositive is like the converse, but it is negated, which by that we mean we make the Q and the P statement, we do the opposites of them. So if we're sticking with this same example about 90-degree angles, the contrapositive would be, again, the converse, if two angles are congruent, then they are 90s, and then we just negate both of those. So we would say if two angles are not congruent, then they are not 90. And so that's a true statement. If two angles are not congruent, then they can't both be 90 degrees. And as it turns out, if a conditional is true, so is the contrapositive. So the conditional and the contrapositive are linked, what we call logically, and that means if one is true, the other one has to be true. And so that will come into play when we start talking about these independent and mutual exclusive events, and you'll see why in a minute. So if a conditional is true, then the contrapositive is true. Remember, the contrapositive is you just reverse the two statements and you negate both of them. So you make them opposites, throw in a not, essentially. Okay. Now let's get back to the statistics idea of independence versus mutual exclusivity. All right, so let's look at this connection between them. There is a connection, but students confuse it often. So let's start with two simple events. So let's assume that we randomly select an adult, okay, from our population. All right, so let's define two events. A being that the person is male, and B, event B is that the person is pregnant. So I think everyone agree that if you are biologically male, you're not going to be pregnant, right? So these are A and B are mutually exclusive events. Okay, so we did a Venn diagram here showing the two events. They're not overlapping. So mutually exclusive, A and B are mutually exclusive. All right, so now let's think about, are they independent? So if we use our rules for independence, we could check. Is the probability of A given B the same as the probability of B? So probability of B given A, given what our A and B are, would mean what is the probability that the person we selected at random, the adult, is pregnant, given that they are male. So we know what that is, because we know that if you are a male, you cannot be pregnant, right? If you're biologically male, the probability that you're pregnant is 0. Now, remember, we randomly selected an adult from our population. What's the probability that that person we randomly selected is pregnant? Well, now it's probably not 0, right? Because some people in our population are pregnant. So that means this part is probably not 0. Those things are not equal. And so these two things are not independent. And so this always happens. If two events are mutually exclusive, they are not independent. So we can write that using some abbreviations. ME gives us not independent. So if two events are mutually exclusive, we know they are not independent. All right, so we have established that that is a rule. If two events A and B are mutually exclusive, then we know they are not independent. And that little squiggly thing here, that means not. So it's the negation of, or mutual exclusivity gives us not independent. Okay, so if that's true, that little mini lesson we just did on contrapositive, if this is the conditional, if mutually exclusive gives us not independence, what would be the contrapositive of that? So we're going to reverse the order of the two and negate both of them. So if mutual exclusivity gives us not independence, then we also know that independence would give us not mutually exclusive. All right, so knowing those two things, mutual exclusivity ensures that we are not going to be independent, and independent also ensures us that we are not mutually exclusive. Let's read through. This is actually from our AP style test at the end of chapter 5. Which of these is true? So for events A and B related to the same chance process, which of the following statements is true? So A, let's see. If A and B are mutually exclusive, then they are independent. Well, we don't know if that's true. Maybe they are, but in this case, we only know for sure these two things. Mutual exclusivity gives us not independence, and so A cannot be correct. It's not always going to be correct. If A and B are independent, then they must be mutually exclusive. All right, well, that would be similar to what we see here, but that would be independence gives us mutually exclusive, and we don't know. That's not necessarily the case, and so we know B is wrong. All right, let's look at C. If A and B are not mutually exclusive, all right, notice that we're not starting with any negations of mutual exclusivity, so we can't conclude anything. Neither one of the statements that we know is true. We always have to start with mutual exclusivity or independence. We can't start with the negations. Those sound like they might be converses, and converses are not necessarily true. All right, so we know C is wrong. If A and B are not independent, so that's the negation of this statement. And again, we don't know what that would lead to. We only know that mutual exclusivity leads to not independence, and independence leads to not mutually exclusive. All right, and so we know D is wrong. And then, so the last one, E, if A and B are independent, then they cannot be mutually exclusive, and that's exactly the contrapositive of that statement that we came up with. So yeah, sure enough, E is the correct answer for that one. Okay, so just remember those two statements. The original conditional we came up with, mutual exclusivity gives us not independence, and its contrapositive is also true. Independent events cannot be mutually exclusive. All right, and so this is your homework for this section.